Hello everyone, my name is Barry van Leeuwen and this is part of the SAC 2021 proceedings in regards to the paper MPC for Q2 access structures over rings and fields. In this paper, my co-authors Robin Jadul and Nigel Smart and I approach the state-of-the-art in honest majority multi-party computation protocols. This was a rather comprehensive approach testing 5 different protocols, each equipable with 3 different pre-processing protocols. And for each of these, 3 different choices of passive multiplication options could be made. To start, consider 4 parties that want to compute a function, say f, dependent on each of their inputs xi, without revealing any of the input to one another. Well, this could be done by handing over the agreed functions and the inputs to a fully trusted fifth party and having them return the answer directly. But the challenge for us in multi-party computation is replacing this assumption of an incorruptible trusted party with a protocol. In this particular paper, we only treat protocols which function for so-called Q2 access structures. To understand what this means, we first define what an access structure is. To do this, we look at the following figure. Here we see all the possible combinations of our 4 players set out. An access structure is then simply a way for us to tell the protocol which parties can retrieve the secret after the computations are done. Let's as an example pose that these sets definitely need to be able to retrieve the secret. This is called being qualified. Then one of the things we require from an access structure is that it is monotonous. Hence, any subset of these qualified sets cannot retrieve the secret, and any superset has to be able to retrieve the secret. If a set cannot retrieve the secret, such a set is called unqualified. However, it can happen that there is a set for which this decision does not come naturally. In this case, the set consisting of player 1 and player 4. Then we must simply make a decision on this to complete the access structure. In this case, we choose to make this set qualified. Such an access structure is then set to be Q2 if the union of no 2 qualified sets constitute the whole player base. This access structure here is actually such a Q2 access structure. One of the major advantages is that this allows us to forego traditional error correcting properties for error detecting properties, so our protocols can be much lighter. Commonly, these protocols work over finite fields modulo a prime, such as SmartWoot 19, or limit themselves strictly to the binary field f2, such as the protocol presented in ABF 17. While there are some protocols that manage to expand this to the ring of integers modulo 2 to the k, as is done in the full threshold case in Speeds 2k and in limited form in other papers for the honest majority setting using simple access structures, these protocols all introduce complex ways to deal with the problem that working over a ring introduces: zero divisors. The problem with zero divisors is that it makes even the most basic things difficult. Take as an example that we want to check if x is 0 or not, while only having a sharing of x and a sharing of a random non-zero element r. To do this, we would normally multiply x and r to obtain a sharing of some element z, and opening z, if this was a field, we would know if x is 0 or not. However, this does not work in a ring because x and r could be zero divisors. By extending the sharings from p to the k to p to the k plus v, you reduce the probability of errors due to zero divisors to p to the negative v. Choosing v large enough then makes this probability negligible. In this paper, we propose how to achieve active security with a board, meaning that when an error or breach of protocol is detected, the whole thing will just stop, for all effective protocols, no matter if they are field-based or ring-based. In fact, we achieve a generalization to any prime power ring for any Q2 access structure, The main idea behind this is that we are able to use extensions to Galois rings with a good Lenstra constant. Colloquially, we refer to these as being L good. A ring is considered L good if it contains at least L units for which the difference with another such unit is also a unit. We then go on to show that if there exists an access structure that works over a field, then the same access structure can be obtained over Z modulo P to the K through the use of Hensel lemma style lifting procedures. However, to gain effective and efficient protocols using these Galois rings, we need an extension to rings of the Schwarz-Zippel lemma. Let f denote a non-zero polynomial of degree d over the ring R. Let R bar then denote a Galois ring extension of R, which is L good, with the set S of size L is above. If one selects R in S uniformly at random, then we have that the probability of f of R equals 0 is less or equal than the degree over the size of the set S. So what is the problem we are trying to solve? Well, we have an online phase in which we want to multiply two sharings, xk and yk, to obtain the multiple zk. This is a simple procedure if everyone follows the protocol. However, when a player decides to mess with the protocol, we suddenly need to make sure the multiplication has been done correctly. To do this, we develop a protocol which takes a secondary triple, both of which we are not sure if they are correct, and consumes this secondary triple to ensure that the first one is correct. To really get an idea of how this works, we will have a look at molcheck 1 in detail. So we start the protocol with two sets of passively secure triples, xi, yi, zi, and ai, bi, ci. Both these triples have to be generated modulo p to the k plus v, and it outputs a single actively secure triple, xi, yi, zi, or it aborts if z is not x times y, or c is not a times b. Note that this output triple is generated modulo p to the k. This is then the full protocol, molcheck 1. One of the particular advantages is that the execution of this protocol can be run in parallel for larger sets through a bucketing technique. However, for the sake of exposition, we will just consider the buckets as containing the triple to check, hence B is 1. For practical applications, I refer you to the full text of the paper where this is extensively discussed. So assume we have the two triples, xi, yi, zi, and ai, bi, ci. Then we let R denote the degree W Galois ring extension over Z modulo P to the K plus V, where V is some security parameter. Then we know that a set S of size P to the power W minus 1 exists by definition of the Galois ring, which will fulfill the conditions of the Schwarz-Zippel lemma. Then each of the parties Pi can agree on a random ring element P, and as we, for exposition, have assumed that B equals 1, the parties can also agree on a random element from S, let's say R. They can then locally compute their own shares, rho I and sigma I, of secrets rho and sigma using the equations displayed. We can then run an open to all protocol to reveal rho and sigma to all participating players after they have done the local multiplication. As all players now have their own sharing and the open values rho and sigma, they can locally compute a sharing of d, di, and use the random value r to compute a local sharing of tau as r times di. Here tau is used wholly as a sort of checksum to ensure that no errors have been introduced to either the triples or the protocol. And so we have shown that xi modulo p to the k plus v times yi modulo p to the k plus v is indeed zi modulo p to the k plus v. And by reducing this result, modulo p to the k, we obtain a secure triple usable in the protocols that we will be using. In the paper, we go into detail on optimal choices of U, V, W, and B. However, assigning P a large prime, K, W, U, and B equal to 1 and V equals to 0 gives rise to the exact sacrifice protocol used in speeds, which is an amazing sanity check. Well, identical except for one point. The cost in speeds is 3 open to alls, while we achieve the same in 2 open to alls by batching parallelization of the openings for rho and sigma. One can observe that we use the Schwarz-Zippel lemma. In step 4a, we generate a random element from the set S, which we in step 4f2 multiply with the sharing di. Note that by definition of di, this should result to 0, and so the degree 1 polynomial computed in this step, where tau starts as 0, should not have any part annihilated, with overwhelming probability. Therefore, once opening 4g, we have that tau is only 0 if di is 0, with overwhelming probability. In the paper, we also present an alteration to this protocol and 2 more protocols which can be used to check the multiplications. However, it may be far more interesting to look at how we ended up applying this. For this, we consider Protocol 4, which is based on the ABF 17 papers and was originally proposed to only work with the binary field. You will recall they used extensive bucketing and shuffling to achieve an efficiency of over 1 billion gates per second. And while this is a very impressive feat, the restriction to the binary field is quite strong. That is why we not only extend this to z modulo 2 to the k, but to z modulo p to the k, so it is fully generalized. And exceptionally, using the ABF procedure does not require us to extend to a base ring extension, so we can do all our computation in z modulo p to the k. This reduces the amount of data transferred compared to many other protocols, leading to exceptional results. Speaking of the results, let's have a look at them. In this table, you can see the 5 different complete protocols, each equipped with the appropriate underlying offline protocol. Each of these protocols was tested on 3 different access structures, 3.1, 5.2, and 10.4 in 3 different situations, the prime field, the binary field, and the integers modulo 2 to the 128. We also tested them with 2 different schemes, replicated or Shamir style. To get a basic idea of the protocols, note that Protocol 1 has an offline phase which produces actively secure triples with the usual beaver online. Meaning we do not have any post-processing as the mul check is used in the offline phase to ensure the triples are actively secure. This technique was coined in KRSW and SmartWood 19. Protocol 2 uses the optimistic approach of both a passively secure offline and online phase to execute the multiplications. Only then it ensures active security by running mulcheck 1 in the post-processing phase. This was first coined in the EKO 20 paper. Directly analog to this is Protocol 3, using a slight variation of our earlier mulcheck 1. See the paper for details. However, this protocol has no need for an offline phase, so no pre-processing is done for this protocol. As described, Protocol 4 is the ABF 17 style protocol using the cut and choose technique in the offline phase, followed by a non-beaver online and post-processing. And lastly, we have Protocol 5, which uses the compute twice technique as coined by Yehuda et al. This has no offline phase and uses double sharings, followed by a post-processing check. This particular protocol is extensively described in the paper because it turns out to be very interesting from an efficiency perspective. Considering efficiency, we were interested in 2 specific measures. The first of which is the online cost. This is simply because a highly effective online phase can be preferable if the costs of the offline phase can be mitigated by pre-calculation or extreme computing power. In this, we observe that Protocol 1 is very efficient because it has no need for a post-processing check to be done online. The other interesting measure is that of total cost, where we have two interesting results. The first being that the ABF style protocol 4 is absolutely the best performing protocol when we regard the total cost over the binary field. However, given that we can generalize it, does not mean that it's going to be as efficient in other situations. Here we observe that the more appropriate choice is protocol 5, which achieves a surprising efficiency when you regard its complexity. All in all, we believe that the most efficient protocols have been identified, and it's very interesting to see for us in what way this can be used in the field. Being able to forego expensive operations by working modulo 2 to the k should be able to yield practical results of some improvement. Thank you for listening.